Okay, so welcome everyone to this video of the Radiation Heat Transfer Learning Journal. In the last video, we just discussed how we are supposed to try and get our divergence of heat flux. So this video, we want to show how this equation, as we integrate the right hand side, will arrive at this kind of an expression. So let's consider the first term first, which is the which is just this k kappa IB lambda. So okay, this is pretty straightforward because IB lambda does not really depend on the direction, neither does kappa lambda if the absorption coefficient is kind of isotropic. So integrating this will just result in 4 pi times kappa lambda IB lambda. So this is pretty straightforward. The next term is of course the scattering term, which is kind of more challenging to deal with because now we have both kinds of integration there. Okay, so how do we do this integration? Now this term sigma lambda over 4 pi we can kind of take out because that does not depend on the direction that we're talking about. So at least we can bring this baby out of the integral. What else can we bring out? Or rather, what else can we do? Okay, what's our next step? Well, we'll notice that the radiation that's coming in from all other direction. Remember, this is the in-scattering term. So the radiation coming in from whatever direction that is not direction I. So this kind of gets messy now. So let's delete this. Okay, so we have our control volume again, and this is what we call dV. So we have two directions, right? One is called direction I, and direction J is whatever is the other directions that is not direction I. Okay, so these are the in-scattering from all other directions. So that's what the direction J is about. So no matter how you change direction I, right? No matter how you change direction I, this the intensity at direction J. Okay, so intensity at direction J. So this is what I'm highlighting here. The intensity at direction J doesn't really matter, no matter how you change direction I, right? Only if you change direction J does the intensity at direction J actually change, right? So only changing direction J does intensity at direction J, okay, intensity at direction J, alright, probably change. Alright, so only changing the direction J does the intensity at direction J change. So what do we have here? We have here this omega I, right? This omega I, d omega I, which is if we take this direction, yep. Remember this is with respect to this dids. So this is dids in this direction, right? And this is si. So this is the IDS in this direction. So this is the direction we're taking. So direction J doesn't really matter. So we can still like bring that we can bring this integral inside, right? Okay, so I'm going to copy and paste this here. And what I'm going to do is I want to put this d omega I in here, because the direction j doesn't really matter. I want to do the integral over 4 pi. Now bring this in. Yes. So yeah, so anyway, you can bring this integral in, and this is what we are left with. Because this direction I is with respect to this dIds, where this is actually dependent on direction I. Okay, so this is direction I, this is also direction I. Alright, so that's why we can bring this in. Now of course, the, what do you call that? This phase angle function, this phase function cannot be, you can't actually bring that out of, you cannot assume that this is independent of direction I. So we'll just leave it here, and you'll notice that, hey, this is what we are left with in this term over here. Okay, so we'll just leave it as this for the time being. Now the last term, so this is term 1, and this is the second term. And let's do the third term. So this, remember, this is a negative term, so I'm going to bring the negative outside. So this is the extinction coefficient, beta lambda into I lambda. So this is the extinction term. Now one thing we need to note, that this is actually dependent on direction I. Okay, so this intensity here is with respect to direction I. So it's not this dIds, but it is instead I as I hat. So the intensity in this direction, not the change in intensity in this direction, but rather the intensity in this direction. So this is also following this direction I here, and this corresponds to omega I as well, on omega I, which is a solid angle corresponding to this direction. So this thin pencil of rays here. So that's how we think about it. So this thing we cannot do very much with it. That's why the integral is left as such. So yes, that leaves us with something like this over here, 10.57. So what is the next step? So we can start from this. So we can actually replace the right hand side with all the terms that we have done. So it's this 4 pi plus this long batch over here, this long batch of terms, and this. Now, is there any way else we can simplify this? Okay, so what we can do is consider this term. The phase function term. Now, if we remember correctly, we're doing this phase function. Okay, we are integrating the scattering fraction from all other angles into a specific direction I. So Remember the definition of the phase function? It is a fraction of from direction j, right? That from direction j into direction I. What is the fraction? So this is direction j into direction I. So what fraction of rays goes from direction j into direction I, right? So if we have one ray here going in direction j, so yes, you have a ray coming from direction j. Yeah, you got a ray coming from direction j. It can scatter in all directions. So in all directions, so remember that the phase function is going from is the fraction of the rays, a fraction of radiation from direction j going into the specific direction I. Now if you were to look at this, this is integrating the phase function over all direction I. So what is the fraction of rays that goes from direction j into all directions? This is, the fraction is 1, right? At least it's the full fraction of everything. So if we were to look at the definition of phase function, okay, look at the definition of phase function. Okay, let's see. I think we were looking at we'll get to, you have to go to our earlier bits. Oh yes, if we take a look at equation 1017. Okay, if we remove this, yeah, look at this. Integrating the phase function over all angles d omega, where omega is corresponding to the direction I, the angle is being scattered into. You do that, you'll get 4 pi. I mean, if you do 1 over 4 pi, you get 1. So for that, it's good news for us because it means a lot of simplification. This is equivalent to 4 pi, right? It's equivalent to 4 pi because that's the, we use the total solid angle as a normalization factor. So since that is 4 pi, very conveniently we can just replace 4 pi here, and of course the inside we can bring 4 pi outside, and that will be just equals to this sigma, and you'll just get the outgoing radiation, I mean the incoming radiation from direction j integrated over all solid angles, right? So this is something we want to introduce. It's called G, or total incident radiation. So let's see whether they have it here. Yeah, 7.59. Okay, never mind. Yes, here we go. G is you can see G is this value here. G, this is the total incident radiation. So remember, the intensity equals to power per unit normal area per unit solid angle per wavelength, right? So if we were just to do a straight integration over all solid angles, we'll get the power per unit area, power per unit normal area per unit wavelength. If you want to be more specific, we can use G lambda. Equals to, it's just the integration as such. Let's make the lambda a proper lambda, and there you go. This is G, which is called the total incident radiation. You see, it's common practice to employ the incident radiation, G eta. Okay, I think it's being defined before, just not sure where in the textbook. Yeah, 10.32. It's called the incident radiation function. Total so incident radiation function, it is this. So this is called incident radiation function. Okay, so that's what G is, and if we were to do this and replace it by G, we will get sigma lambda G. Okay, a simple G lambda. Okay, so G is just integrating the incoming radiation from all sides. So sometimes you see this sigma lambda is equals to sigma S lambda. Some notations use sigma S lambda, but they basically mean the same thing, the scattering coefficient. So having a sigma S does denote that the sigma is referring to the coefficient of scattering or cross-section of scattering. Okay, so this is what sigma lambda is. And okay, going back to our divergence, we will get a very simple looking formula. Okay, so let's take a look. We just go back to our equation there. Okay, so let's take a look back at our RHS. So the right hand side is this, and we can simplify this to sigma lambda G lambda. Alright, and what else? Okay, we can still simplify this a little bit more. So previously I said we could not quite bring beta out unless beta is like independent of the direction. Now if it's an isotropic material, that might not be true, but most mediums, at least for most mediums of our interest, we can bring that out. So it's we can bring this out since this is like not quite not quite what we need. Okay, so what's next? Okay, anyway, so we notice that this expression here is also G. It just uses a different direction, SI instead of SJ. But since we are integrating over all angles, it doesn't really matter whether it's SI or SJ which we are integrating over. It will still be G. So the right hand side kind of reduces a lot to this. Now, so remember, okay, what is the there is we can actually factorize G out of these two, and what we'll get is something like sigma lambda minus beta lambda G. Okay, so what is this then? Remember, beta lambda equals to sigma lambda plus kappa lambda, right? So the extinction coefficient is equals to the scattering coefficient plus absorption coefficient. And well, if we were to rearrange, we would just get sigma lambda equals to beta lambda minus kappa lambda. Altogether, we will just get this quantity is actually minus kappa lambda. I'm not going to do the proving, but I mean it's just simple addition subtraction. And if we were to factorize kappa lambda out, we will get something really very simple. 4 pi I b lambda minus g lambda. Okay, so this is the divergence of our heat flux. Nabla bullet Q radiation. And remember, this is the heat flux vector, not the heat flux scalar that we were talking about earlier. That is just equals to kappa lambda for pi IB lambda minus G lambda. So remember what I was talking about, the physical meaning of this radiative divergence of heat flux. This is the net heat that's going out of the system, out of this little control volume. And if we were to take a look at these terms, this is actually, you know, the total amount of radiation that it's being emitted. Okay, this is the total radiation being emitted. This is the total radiation coming in. So I mean, there's this kappa lambda, which is talking about the absorption coefficient, which you can think of it as some kind of emissivity. So there'll be a fraction of, let's say, G lambda, which is absorbed, which is the fraction of the incident radiation being absorbed, and the fraction of the incident radiation being emitted. And notice scattering doesn't really matter because we are taking it over all angles. So since that doesn't matter anymore, scattering kind of disappears, which is nice and convenient. Okay, so this is what the divergence of heat flux actually looks like. Now, of course, this is relatively easy to calculate. The IB lambda, if we know the temperature. G lambda is a little more challenging to calculate, but at least we have some kind of function. We have some kind of very simple looking equation here to describe the total heat output from a unit volume of dV for our participating medium. Now, of course, there's a special case. We call it radiative equilibrium, where the divergence of heat flux is 0, but that one we can talk about next time when we talk about solving cases. So now we know how the expressions for divergence of heat flux and heat flux actually looks like. Okay, where is it? Yeah, this is what our heat flux equation looks like for, if you're talking about surface at the boundary. This is what the divergence of heat flux looks like, which is the total amount of heat output per unit volume. Okay, so yeah, so these are the things we really want to calculate. These are the things of interest we want to calculate when talking about using the radiation transfer equation. So next video, hopefully, yes, we can finally start looking at some more interesting things where we talk about actual exact solutions using this integration thing. So the basic ideas are we need to consider a 1D case. Okay, 1D case, that means using a plane case. Plane is in the Cartesian coordinates. if we can also use spherical or cylindrical mediums. No, that's a lot more challenging even for 1D, but that's what we want to talk about in the coming videos. Yep. So see you next time. Thanks for watching. See you there again. Bye bye.